do them, and I'm just deciding which 3 labs I want to do. I just haven't quite made my call yet. So I will get to, I promise. Okay, so what are physical versus chemical reactions? A chemical reaction, and you should have known this from grade 9, but if you don't, that's fine. You're going to know it now. A chemical reaction, you might have had me in grade 9, in which case you might not know much of anything from grade 9, and that's okay. A chemical reaction is one where atoms and compounds are rearranged. So that could mean taking lone atoms and putting them together to make a compound. It could mean breaking a compound up into its lone atoms, or it could mean taking 2 compounds and sticking them together. Learned a lot about that in biology, right? Taking big molecules and making chains of them. It could mean taking 2 big molecules and having them swap things back and forth. It could look like a lot of different things. We're going to look at some prime examples in this course of types of reactions, but of course, it could mean a lot of different things. We look for physical changes as indications that chemical reactions have taken place. What are some of the things we'd often see? Somebody mentioned a change in color. I liked that. We got change in consistency and texture. That definitely can happen. I'm not going to put here as sort of a key one that we look for in this course, but it's definitely a good, legit answer. What are another couple signs of chemical reactions that we'll see a lot of? Yeah. So changes or new smells, sure. If you take grade 12 bio, grade 12 chem, we do a lab where we make esters. And it's neat because you start with all these chemicals that smell like crazy potent chemicals, and then all of a sudden you're like, banana? Strawberry? It's weird. We make fruit smells out of seemingly not very fruity elements. For sure. What else might you see? Sorry? Yeah, that's right. You could get gases forming. And if that reaction is happening in a liquid, that would, of course, look like bubbles. What else? Whoa. What's that? What about temperature? Change in temperature. What's that symbol? Yeah, that means change. And of course, T stands for temperature. It's a good thing to remind ourselves. What else might you see? Gases could form. What else could form? Could a solid form? Sometimes you mix 2 liquids together and you get a solid forming, which could potentially be a sign that a reaction has happened. We call that precipitate. Now, just to be clear, these things don't always mean that you've made a chemical reaction. If you boil water, it bubbles. That's not actually a chemical reaction. You're just heating water up. You're just freeing it. If you cool ice, or cool water, it will form ice, which is a solid forming, which again isn't a chemical reaction. It's still just water. So these things don't definitively mean that a reaction is happening. They're indications that a reaction has happened. By the way, there could be sound, there could be light, right? Imagine an explosion. That's a chemical reaction. What would the signs of it be? Well, a change in temperature, gets hot. An explosion would also have a change in, what's P in this case? Delta P, pressure, change in pressure. Right? An explosion also has a big pressure wave, right? It also makes a change in color. Yeah, pre-exploded. It could produce light. Just things to watch out for. When we do our labs, we'll see variations of all these. There could be sound. right? That's possible. Explosion makes a lot of sound. Again, none of these things means definitively, oh, I heard a sound, a chemical reaction happened. Well, maybe. Maybe somebody was talking. Maybe there was a speaker, right? But it's an indication. It's possible. Okay. The key is that all of these are just things that could potentially indicate what has actually happened. And what is actually happening in a chemical reaction? We're taking molecules apart, or we're pulling ionic compounds apart and putting them together. Or maybe we're taking individual atoms and pushing them together into compounds. Or we're taking compounds and switching things from them. We are changing building blocks. Taking things apart or putting things together. Or a bit of both. That's what chemical reactions are. Okay. The other way we could say this is we could say that bonds are broken or formed. A chemical reaction happens anytime bonds are broken or formed. Doesn't have to be both. It could be either one. Breaking bonds is a chemical reaction. Making bonds is a chemical reaction. Doing both is a chemical reaction. And again, what are the two types of bonds we learned about? Very good. Within covalent, we kind of have two more categories. Does anyone remember those? In a shared case, you can have kind of two different types of sharing arrangements. Polar and nonpolar, which is where you have equal sharing or unequal sharing. Which is which? Polar bonds are when they are unequal. And nonpolar bonds are where they equal. Good. All right. But there's a rule that comes with that. And the rule is this. We call it the law of conservation of mass. And it says this. In any chemical reaction, and you're going to see this short form a lot, so I'm just going to start using it right from day one. No new atoms are created, nor are any destroyed. And we can kind of say this in a couple of ways. One thing we could say then is, to do a little bit of math, therefore, the mass of the reactants must be equal to the mass of the products. What do those two words mean? Those two new words, maybe, or maybe you're comfortable with them. What do they mean? Sorry? Yeah. Do you know what my favorite kind of chemistry is? I like all chemistry. Chemistry teacher, fan. I like some more, I like some less. Do you know what my favorite kind of chemistry is? And this isn't a joke. I'm being dead serious about this. Cooking. I like food. I'm a big fan of food. Maybe a bit too big of a fan of food. But that's okay. I'm a big fan. But I'm not joking when I say cooking is chemistry. Cooking, now, not making a salad isn't chemistry. Well, even it is a little bit, but mostly there you're just kind of putting stuff together, but you're not really changing things. But as soon as you apply heat, as soon as you put something on the stove or in the oven, you're changing things, right? In other words, the lettuce that's still, on the stalk and the lettuce that's in the salad, same lettuce, right? But uncooked chicken and cooked chicken, different thing, right? Flour and water mixed together with a bit of yeast and salt, very different from bread, right? These are not the same thing. Cooking is chemistry. It's delicious chemistry. And I had a good friend who went into food science as a field and works for a big multinational food company because, cooking is chemistry. And we use chemistry to kind of enhance cooking. But in cooking, we have another word for reactants, which is what? Ingredients. But it's the same thing. Does that make sense? When you set out to cook, you have your ingredients, and then what you get is the product. In chemistry, we just have another word for ingredients. We call them reactants. But don't overthink it. It's just ingredients. These are just the things you put in.
Please excuse this interruption. Fasten students. At this time, everyone who has been excused on attendance for the job fair should make their way down to the lobby. So teachers, you will know students excused if there are students as excused. So please send those students down to the lobby to 4C5. Any spots open up, we will let you know. Thank you.
Now this is true. The mass isn't going to change. If you start with 20 kilograms, you're going to end with 20 kilograms. That is true when you cook as well, by the way. Now, that doesn't necessarily mean that, your bread is going to weigh exactly what your dough weighed, because things can float away, right? Things can, if things become a gas, and remember, we said that's one of the things that can happen, it might be very hard to keep track of that. Did you guys do in grade 9 or in grade 10? This is a lab I usually do in grade 9. But then again, you guys had a weird grade 9 year, but where you do like baking soda and vinegar, but the challenge is don't lose any of the mass. Did you do that? Did I not do that with you guys? This is a little challenge lab I do. We could actually do that in this class. Might be a fun little one. But it's just who can, if you weigh your baking soda and you weigh your vinegar at the beginning, and if this is true, and this is true, you shouldn't lose anything. But of course, if you just do it in a beaker and weigh it after, it's going to weigh less. Why? When you put baking soda and vinegar together, it makes a gas, carbon dioxide. And if you just let that go, you're going to lose weight, right? So the question is, how could you trap it? And people come up with all kinds of different ways. Usually, the clever ones discover very quickly.
Good morning, Eagles. At this time, everyone who has been excused to attend the job fair should make their way to the lobby. Teachers, you will know students have been excused if they are excused on the attendance. If you have any questions, feel free to call down to the office. Thank you and have a great day.
I hope there's a few more announcements about this. I feel like I don't quite know what we're doing yet. That was snarky. See that? That was snarky in a way I didn't mean it to be, and I felt rude. Anyway, and usually the clever kids discover quickly that if you just put a balloon over the top of a beaker, then, all that gas will get trapped in the balloon as long as you have a good seal. You weigh it before and you weigh it after. It weighs the exact same. All right? But there's another classic example of this where even on a bigger scale, somebody did raising plants and weighed everything, including all the gases that were let in, right? Like weighing all the CO2 that was allowed into the chamber and weighing all of the O2 that was released. So keeping track of everything. And you discover that in any system of reactions, if you weigh all the stuff at the beginning and you don't lose anything and you weigh all the stuff at the end, it's going to weigh the same. Matter doesn't go anywhere. It doesn't disappear or appear. It just moves from one thing to another. Does that make sense? But it doesn't just mean mass. The corollary of this, the exception of this is all your starting atoms will be the same as your ending atoms. They might be in different places, but you'll have all of the ones that you had. Nothing's going to go anywhere. We want to remember that anytime we do chemistry, because it's easy to forget and just kind of throw the equation down and be like, oh, I started with this and this and I ended up with that. Great. But then we got to make sure that our reaction hasn't lost anything. What do we call that process of checking to make sure we haven't lost anything and seeing how the reaction might have to be adjusted to make sure it accounts so that nothing gets lost? What do we call kind of the chemical accounting of a reaction? You must have done a lot of this in grade 10. This is like usually the thing you do a ton of in grade 10. You take equations and you balance them. Did you do a lot of balancing practice? Use a lot of worksheets. There's like little fill in the blanks. Usually it's like balances. Hi. Mm-hmm. That's fine. Send it to me and I will. So, if you hate it last year, don't worry. You'll love it by the time we're done this year, because last year you had like probably 2 weeks to do it and then you had to like be done with it, right? And you're like, oh shoot, I never got good at this. The same reason I'm not worried if you're struggling a bit with Unit 1 right now. I'm really not. Nobody's in the like, holy crap, they have no idea what's going on zone. And so I know you're all going to get it with a bit more practice. Likewise, when it gets to balancing, if 2 weeks isn't enough to get good at, that's cool. I promise the 3 months we're going to do it here you'll be good at by the end. I promise. Not the least bit worried. So let's talk reactions. Often we will do what we call a word equation. This is just a description of the reaction. Yeah, joseph.orlando@dsbn.org. And if you come here, I can even type it in. And it lists reactants and products. Again, ingredients and products. All right, we'll give a simple example. And let me quickly go to the next page to remind myself what I end up using as my example. Yeah. Sodium metal and chlorine gas react to form, and here's one you should be able to figure out really quickly. We have a lone sodium metal and a lone chlorine gas. And of course, if you put them together, we have sodium as a metal, chlorine as a non-metal. What are they going to form? An ionic compound. And I bet you can tell me the name of that ionic compound just real easy. Yeah, beautiful. Sodium chloride. All right, so that's a word equation. Sound my way? Great. All right, let's go.
I made a new resume and such, but the website, I didn't realize that it was like it was like a trial website. It said free, so I thought it was. And then I went to send it and it charged me, so I used my old one.
That's fine. I'm just gonna quickly get it onto one page because you don't want two pages in the. Oh, no problem.
Sorry, I didn't even get a moment to edit my.
You're fine. You're great. It looks nice. Okay.
I had the right idea on my old one.
Yeah, that looks great. Okay, so sodium metal and chlorine gas react to form sodium chloride. We all got that down? Great. So now, how do you turn that into a balanced chemical reaction? Well, the step one is just write all of these out as their formulas. So we need to know what sodium is, we need to know what chlorine is, and we need to know what sodium chloride is. So for a moment, I just want you to work each of those out. And you'll never go through this step-by-step process again, but that's okay. I want you to tell me the formula for each of these. All right, so take a minute, do that. So we said sodium and chlorine gas form sodium chloride, so we need to know the formula for each one. So do that. Once we've done that, then we'll be good to go. I just want to move fast here. Oh, I see what I'm doing here. So if I just take that out, remove space before, and remove space before. We're real close. Beautiful. All right. Just page and
Oh, top of the morning to ya.
sorry?
I said, oh, top of the morning to ya.
If I'm,
Is she here today? Or do you have her?
she's not on mine, no.
Oh, they told me she was in one. Oh, sorry. I am looking for. Never mind.
I didn't see today.
Oh, okay.
Yeah.
Maybe I'll see him this afternoon. Okay.
Yeah.
Okay, thank you. Sorry to interrupt.
No, and don't be sorry at all. Okay, so guys, trivial, of course. What's sodium? What is it? Okay, and if it's a metal, what should I probably say about it? We're going to kind of build this as a habit. We're going to describe things in our symbol. So a metal is, we usually put the state of matter here. What's the state of a metal? As a rule, at room temperature. Yeah, obviously, we could make it a liquid if we got it hot enough. We could even make it a plasma, a gas, if we got it even hotter still. Maureen, here you go, kiddo. No problem. Anytime. Yeah, you too. Chlorine gas is obviously including its state. Sorry? All right, everyone stand up. Up, everyone up. Everyone up. Everybody up, come on. Guys, individual chlorine atoms, you find a lot of those floating around? No. Now, sodium we can get one atom at a time because it is a crystal. It's a metallic crystal, which means that it can exist by forming what we call this weird continuous syncytium of electrons. One sodium atom can share with all the other atoms near it, and so you can get sodium metal, and you can peel one atom off at a time. But chlorine, how does it exist in nature? It's a gas, so it's not sharing with anything, right? Gases are individual particles floating around. It's two of itself. It is, what's the word for that again? Diatomic. Thank you. So, given that chlorine is diatomic, it might behoove us to remember what are the diatomic elements. What are the diatomic elements? Hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine. All right, all together, team. What are the diatomic elements?
Hydrogen.
That wasn't good enough. What are the diatomic elements?
Hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine.
C minus, sit down. Okay. All right, listen. Shh. This is important. It's important because as we start doing chemistry where we actually have to weigh stuff out, having twice as many atoms makes a difference, right? So this isn't just me being pedantic and miserable and being like, "Rah." It's going to make a meaningful difference because when you go to weigh out the sodium you want to react with your chlorine gas. I don't know how much you know about chlorine gas, but if I'm working in an industrial setting, do I want to accidentally have twice as much of it as I think I do and end up with half of it being left over? Chlorine gas, famous for being nice, friendly thing to have around that's cool and fine and safe, and yeah, great, we love it. Yeah, precisely. So these things matter. Like, this isn't some esoteric thing. Chlorine doesn't exist as individual atoms. It exists in diatomic state, which means that when you do your math with this, when we do an equation, we have to account for that, which means when we come up with its formula, we need to account for that. Now, sodium chloride, I know you all know this one, but we're going to build a habit here. Every time you figure out the formula of something, you're not just going to say, oh, sodium and chlorine. We're going to remember, oh, yeah, we know how to find the formula of an ionic compound. Sodium takes what charge? +1, right? If we had the table in front of us. And does anyone remember off the top of their head what chlorine takes as a charge? -1. And now, here's my question. This is where we always get, can I tell you what people do? And you're all going to, well, not y'all, most of you at some point will do this. You'll go, right, okay. So I've got that. I promise. Because it's just instinct, right? Like, oh yeah, that and that. But no, we know how sodium and chlorine come together, and they're big dumb rocks, so they can only come together one way. And when they come together, it's based on this, not based on what the reactants are. This is where people get screwed up. What the reactants are tells you what the product's going to be, but it doesn't tell you the formula of the product. How do you figure out the formula of the product? The same way we figure out the formula of the reactants. The same way we figure out the formula of anything, you have to work it out. Does that make sense? In this case, it's trivial. This is not going well. That's a 1. It works out, and the formula of sodium chloride is NaCl. But we don't just randomly do that. It's worked out every time. You're going to be doing this either actually on the page or in your head a lot. So, in fact, I on the test I toyed with putting these charts next to the table, but then I was worried for the ones that were covalent that people would think this applied. I didn't know how to approach it, but a good idea. Now, to turn this into a balanced equation, just write it out. When we say we have more than one thing, we just use a plus sign. That's the and. And when we say the reaction happens, we show that with the arrow. All right, that's what these mean. So how do I write this as an equation? Well, if this is the reaction, what do I start with? What is the beginning before the reaction happens? Yeah, we have sodium, and it's a solid. And we have chlorine, and it's a gas. And we didn't mention this, but sodium chloride as a rule, if we're working under normal conditions, will also be... It's an ionic compound. What do we know about ionic compounds? Big stupid rocks, so it's probably going to be solid in this setting. Now, sodium chloride dissolves in water, so it'd be easy to end up with dissolved sodium chloride, though in this case, it looks like we're working with solids, right? So, all right. That's an equation, and we're done? No. Why aren't we done? But why do I need to balance it? Like if we literally look at this, if I were to draw this out, what it looks like is this. So here I have my lonely little sodium atom. There he is. And he's reacting with chlorine gas. And chlorine gas we know is diatomic, right? So it looks like that. And chlorine just makes a single bond. So there we are. And the reaction's going to happen here, right? And what we end up with is, I had green all along. That looks much better. And what we end up with is these two things stuck together, okay? But what's the problem? Where does this go? Now, are we going to get just a chlorine atom floating around on its own? Why not? Because the whole reason it wasn't floating on its own to begin with is when it's on its own, it's not stable. So this wouldn't be a favorable reaction. This wouldn't happen because this would leave things in a less stable state than they started. Because sodium can be stable on its own. Even if it's not super stable, it's a little bit stable on its own. Chlorine cannot be stable on its own. It just can't. It forms diatomic. So we're not going to move into a less organized state. So for this reaction to happen, it can only happen if there's enough sodium to get the job done. And looking at it visually, what's enough sodium to get the job done? You need two of them. You need a second one. Oh, that's the wrong color. You need a second one here that can bump into that one. And now we can get a favorable reaction. Now, are we going to draw a reaction out like this every time we need to do one? No, that would be ridiculous, right? But hopefully drawing it out kind of shows you the principle. Does that make sense? We can't leave something partially finished. Every reaction, if it's going to happen, has to happen so that everything gets used up. Everything that was a reactant ends up as a product. And the only way we can change the reaction is by changing how much of stuff we have, how many things we have. Does that feel okay? We can't change what it is. Like, obviously, the easiest solution would have just been to say, well, why can't it just take... I'm going to tear that PA off the wall, I swear. Like, this would be the easiest solution, but what's the problem with this? This would be NaCl2. And does NaCl2 exist? No, why not? Because that would require sodium to give 2 electrons away, and sodium doesn't have 2 electrons. You can't change the products because we know how we figure out what products are possible, and NaCl2 isn't a possible product, only NaCl. So this can only happen if there's a couple of sodiums around so that they both can make this reaction happen. Does that make sense? We're cool with that? Okay. By the way, this is easy to make happen because sodium is a metal, and normally they're all stuck together. There's a bunch of them. So when this chlorine gas hits the metal, it's fine. It just doesn't tear away one sodium. It tears away two sodiums. Does that feel all right? It's not too bad? All right. Now, how do we do that here? Well, here's what I recommend. We have sodium. It's a solid. Reacting with chlorine. It's a gas. And we need to produce sodium chloride. Just count. Just count. So right now, let's take a look and see how many atoms are on each side. How many sodium atoms are here? 1. How many chlorine atoms are here? 2. And then on the right side, how many of each? 1 and 1. Okay, now, hopefully, I didn't teach you grade 10, and Elastic seems like a nice guy. But hopefully he was mean about this. When I teach grade 10 science, and again, I do so very poorly, but one thing I scream at people all the time is, when you balance an equation, you're only ever doing one thing. Just only one thing. There's only one thing you can do. You are counting. Listen. Okay. If you had a factory, that made cars, and you went to make a car, you're putting all the things on, and you're like, oh, this thing needs 4 wheels. And then you looked, and in front of you, you had all the parts. Maybe not a real car, because that's complex thing. Maybe you're making little toy cars. Right? Can you picture that? You're a little toy car factory. Maybe they're made out of wood. Toys aren't really made out of wood anymore. But, imagine like back to a crappy time when toys were made out of wood, not out of phones. Now, if you were like, oh shoot, here I am making this car, and all I have is 1 wheel, would your boss and the buying public be happy if you went and got a saw out and cut that wheel in 4 so that it worked? And pretty stupid, right? Would the boss be happy if you said, I'm just going to change the final design of the car so it only has 1 wheel? It doesn't make any sense, right? If you think about a reaction as a recipe, if you said, okay, I've got this in front of me, and here I've got a cup of milk and 1.5 cups of flour, and over here I have only 1 egg, and the recipe calls for 5, but that's fine, I'm just going to use the 1, so I'm just going to change what the finished product is, and it's just going to be, this same cake, only with a quarter of the eggs necessary and 6 times as much sugar, because that's what I had to start with. Would that be cool? No, right? Like your boss would fire you. So look at me. You're not changing the stuff. You can't change the things. If you're a baker, the only thing you do is change how many of each thing you use to make how many of each thing. That's right, you're not taking a note right now. Let's put that on the table behind you, all right? So you can't change the things. Look at me. You're never going to put a number here. You're never going to change that number there. You're never going to put a number here. You're never going to put a number there. All you can change is how many things you have. You can't change the stuff. And in a chemical reaction, there's a place where we put the count. Where does the count of how many of these you have go? In front. The only thing you do when you balance chemical reaction is you put numbers in front of these things. In grade 9 and 10, we usually facilitate that by like putting a box here that says like put a number here, right? But this is what's changing. And what is that number? It's the count. This is a sodium atom. You're going to tell me how many of them we need. This is a chlorine molecule. It is Cl2. You can't change that. That's what a chlorine molecule is. All you're going to do is tell me how many of them you need. This is a sodium chloride ion, or formula unit. That's what it looks like. You can't change it. You can't make it NaCl2. Yes, that would balance it. The problem is you've balanced it by telling me you made something that doesn't exist. That's not useful. What you can tell me is how many of these are going to get made. Does that make sense? You're just balancing. That's what it is. That, by the way, is also, if you work in a kitchen, how recipes work, right? Like if they say, hey, you need to scale this recipe up because we need to make 100 servings tonight. You change all the things by changing how many of them you use. You don't change the stuff. You change the count. You change the amount. Does that make sense? So, when we go to balance this, we say, okay, right now, sodium is balanced. Good. The problem is right now, chlorine isn't balanced. So what do? Well, I wish I could do that, but can I? Oh, guess I could do that. I wish that I could do this, but can I? No. So there's only one thing I can do. I need 2 chlorines so I can get 2 sodium chlorides. Now I will have 2 chlorines, right? Because each of these has 1, and how many of them do I have? 2. So now I've got 2 chlorines. But what else has changed? Because I gave myself 2 sodium chlorides, I have 2 chlorines, but I also have 2 sodiums. So they both change, which means that now my chlorines are balanced, but my sodiums aren't. Does that make sense? So what do I do to balance the sodium? Well, that's trivial. I would do this. And now we're balanced. I think I would. Pretty sure I'm the science teacher. A degree in chemistry. Okay, smarty pants, where's it go? In front. And now that's balanced. So now listen. What this means is, to read it, the number in front is always a count. I have 2 sodium atoms. What's a sodium atom look like? A single sodium atom. That can react with 1 sodium molecule. What's a sodium molecule look like? The chlorine molecule, rather. It's 2 chlorine atoms stuck together. 2 of these reacts with 1 of those, and it will give me 2 of these. And what's one of these look like? It's a sodium stuck to a chlorine, 1 to 1. That's how you read that. The number in front tells you how many of the whole thing you have. The numbers in the thing tell you how many of them are in each one of these. If you were using this as an analogy for my stupid little toy car, you could say body plus 4 wheels gives a car, and in chemistry, that'd be written like this. That would be a car. What's a car? Car is body wheels for. Now, kind of a weird thing to say, but does that make sense? This is a single car. What's a single car made up of? It's made of a body and 4 wheels. When we get the equation, it'd look like this. Body plus wheel. I guess that wouldn't be pluralized. It's not like we pluralize sodium. I need to make a car. What's a car? A car is a body wheel for. Okay, how do I balance this? Well, I'd say bodies and wheels. Right now, on the left side, I've got 1 body and 1 wheel. On the right side, I've got a body and 4 wheels. What's out of balance? The wheels. So I just have to say, that's fine. I need 4 of them. Does that make sense? You do this with anything. You could say, okay, how do you make a sandwich? I don't know. A club sandwich, complicated sandwich. Ooh. Because what do you need? A final club sandwich is 3 slices of bread, just to be confusing. Yeah, there's one in the middle. Traditional. And then you've got either chicken or turkey. We're going to make a turkey club. And 2 slices of that, the restaurant I worked at most recently. And then bacon, 3 slices, right? And then, what else is on it? Tomato slices, 2, and lettuce, we'll just say 1 piece of lettuce. Does that make sense? That's like what this is, and you'd have to put all of the ingredients over here, and you could say, we need 3 bread slices. You don't have to write this, by the way. I'm just kind of showing the idea. Plus 2 turkey slices, plus 3 pieces of bacon. Does that make sense? That's what we're saying here. Me too. I'm always hungry. I spend my whole life hungry. And a club sandwich is a superior sandwich. It's a good thing. You could ask for no cheese. Well, I can't help you with that. That's an existential crisis. But does that make sense? When things are put together, we write them together, and how many of them we are in that thing are put as little subscripts. The thing in front counts. And then, if somebody ordered If somebody said, okay, hey, we're sending you an order for 6 club sandwiches, well, that would go in front, and then you'd have to change all the ingredient numbers to make it work. Does that make sense? That's how balanced equations work. All right. Let's look at an example. In fact, we'll look at a couple. Let's look at the simplest possible reaction. We just did one. The simplest reaction is you take a couple of things and you smack them together to make a new thing. And we call that a synthesis reaction. Okay. We just did an example above. Let's do another example. Let's say, I don't know. Let's say we had some zinc metal lying around. What am I going to put here? It's solid. And let's say that we go over to the Bunsen burner and we heat it up and we let some of it react with the air around us. What in the air is it almost certainly going to react with? Because that's what things do. Oxygen. And that, of course, looks like that. Clever people. What's it look like? O2. Oxygen, of course, is diatomic. Okay. Now, what's that going to form? I don't know why I picked oxygen here because I was going to do that below, but that's fine. What's that going to form? Zinc oxide. Now, what do I need to know before I can do this? This is what our product is going to be. We know that because when zinc and oxygen come together, they're going to make zinc oxide. But I can't turn that into a balanced equation unless I know zinc oxide's formula, right? So we need to work that out. What charge does zinc take? Is it 3+? I think it is, but I always get zinc and aluminum stressingly. No, you know what? It's 2+. 2+. Okay, so that's good. So it's a nice, easy one. Zn 2+. And what's oxygen? -2. And so this is trivial. What's the formula going to be? ZNO. Very good. All right. And by the way, guys, do we see what I just had to go through? I had to work it out, right? I didn't know. I didn't just throw them together. I had to go to the right and work out the formula. You're going to do that every time. Every time you get a compound, you got to figure its formula out. That's why we do that in the first unit. Now, what state of matter will that probably be? Ionic compound, so it's a big dumb rock. It's going to be solid, right? In fact, it's probably going to look like a little deposit on the surface of your zinc. It's going to look like oxidation, rust, metals rust. Okay, but now, this is neither here nor there. Is this balanced? It's not balanced. Why isn't it balanced? Well, because there's only 2 things in here. We've got zinc and oxygen. And on the left side, we have how many of each? 1 zinc and 2 oxygens. And over here, I have 1 and 1. This is a very common balancing structure. This looks a lot like the last one. How am I going to balance this? Right now, what problem do I have to fix? Do I have a zinc problem or an oxygen problem right now? I have an oxygen problem. How do I solve that? Well, I guess I could do that. Why not? Because there's no such thing. ZnO2 isn't a thing. That's turning a car into having 6 wheels because you had 2 wheels left over. It makes sense, right? Can't drive it. So the only thing I can do if I want to double up the amount of oxygen I have is do what? I can put 2 in front. That makes this into a 2. But what else does it change? The zinc, which means I have to do what? It means I need to put a 2 over here as well, and now we're balanced. All right, bit of practice. I can help you. Oh, you all done?
Yeah.
Beautiful. Yes, absolutely. Please. All right, and these follow the general form. Well, they follow the general form of something A plus some other thing B yielding some new thing AB. Now listen, you don't have to look at me. Look at me. Is everyone looking at me? Is everyone looking? You don't have to write this. In fact, please don't. Though if there's any algebra freaks here who would rather do balancing equations as algebra, that probably won't be most of you. How many of you love algebra and think you have phenomenal algebra skills? Well, if you wanted to, this would be trivial because this may or may not have a subscript, right? Let's just start with M and N. and this could be X or Y, and then we could call this Q, R, S. And you could totally just set up an algebraic equation and solve this, right? You could just, and again, I hope you're not writing this down unless you love this, but if you really want to, it's trivial. You could say, well, how many A atoms do I have? Well, on the left side, I have MQ A atoms, and over here, I have XS A atoms. Those have to be equal. And then how many B atoms do I have? Well, here would be N times R, and over here it would be Y times S. And you figure out M, X, N, and Y by actually just knowing the equations of things. And here you have a system of linear equations, and you just substitute and solve. Easy, trivial. So if that's how you want to balance chemical equations, easy to do. Not how I'm going to teach it, but something to keep in mind. Now again, for everyone else, let's not write that down. They follow this form, right? But keep in mind that what we don't know is all of this other information. Does that make sense? The question marks you can write. This is all the stuff you have to figure out. Does that make sense? And in fact, I'm going to color code my question marks because we'll talk about the two different ways we get this missing information. That looks too much like the other. I should use like a nice... that's a good choice. I like that. All right, to get all the green question marks, we have to do that by knowing the formulas of products and reactants. All right, that's what we did up here. You have to go to the side. You have to know everything's formula. How did you know this formula was O2? Well, I've made you memorize the diatomic elements. You have to know which ones get the little 2 and which ones don't. So that you just get by knowing. And then how do we figure out the numbers in front? Well, that's where we have to balance the equation. Does that make sense? Though again, you could replace this balancing. If you want to do some algebra, Go nuts. You could train a computer to do it. I've trained my computer to balance chemical equations, and it even works most of the time. But sometimes it goes horribly wrong and gives weird answers, and it makes me very sad. And you know who wouldn't have it go crazy and do weird things? Galford. That guy'd figure it out in no time. Now, I want to talk about a few key cases, things you'll come across. First of all, metal and oxygen. I want to make a note here. These are entirely predictable. This you should be able to predict. In other words, if I gave you any metal on the periodic table and oxygen, you should be able to tell me what the products will be. And of course, you know why that is. What kind of compound is this going to be? Yeah, because it's ionic. Right? Because a metal and oxygen will make an ionic compound, this is going to be entirely predictable. Yeah, since actually, or while, but yeah. So this is very, very, very easy to work with. If you do a metal and oxygen, but let's look here. Let's pick, we just did zinc. Let's do aluminum. Aluminum, and of course, aluminum is going to be a... Actually, let's not do aluminum. Well, yeah, I don't want to do aluminum right now, actually. Let's do, as boring as it is, let's do potassium. That's better. Let's do potassium and oxygen. This is one nice, easy example for where we go from here. What's that going to form? What's that going to form? It's going to form potassium oxide. And of course, what am I going to need to know about potassium oxide? Yeah, I'm going to need to know its formula. So we go over here and we say, okay, what is potassium oxide? Well, I know what potassium is. I know what oxygen is. Do I know the charges they take? What charge does potassium take? It's +1. Very good. If you didn't know that, that's okay. Where would you look? Periodic table. Oxygen is -2. And again, that's okay if you don't know it. Where would you look? On the periodic table. If I have one of each, does that balance out? And as soon as I get 2 potassiums, all of a sudden we discover that it is totally fine. So what's the formula of potassium oxide? K2O. All right. Is this a balanced chemical equation? No. How would I balance it? So, listen, don't get confused. Slow down. Just slow down. And if it helps, draw it. Okay? For now, let's draw this. Okay, I've got a big sheet of metal here, right? There's a sheet of metal. It's potassium. Oh, look at me. I'm potassium. Hey, okay. And then what's bumping into it? Oh, I've got an oxygen atom here. Okay, there I am. I'm an oxygen atom. And I'm going to bump into that potassium. When I do, I'm going to scoop up potassium atoms and react with them, right? What does the end product of this look like? Well, you just told me. An oxygen atom is going to have 2 little potassiums on it, right? That's what potassium oxide is, right? But how many potassiums did I start with? 2. So I'm going to have to end with at least 2, right? I could maybe start doubling it up, but at least 2. So it's going to look like that. Well, for that to happen, okay, how many little potassium atoms did I have to scoop up? How many atoms did I scoop up? How many potassiums? 4. So you can go back here and look and say, okay, I'm going to need that one, and maybe that one, and that one. I'm going to need 4 of them, right? So now count what you had. How many oxygen atoms did we have? 1. 2 atoms, but how many molecules, right? 1O2, which, yeah, is 2 oxygen atoms, right? Okay. How many Ks did I have? Well, I had that one, and that one for a total of 4. Right? And that's 4 atoms because each of them is just 1. And then altogether, what do I get here? How many K2Os do I get? 2, which is 2 oxygen atoms, right? And 4 K atoms. And can everyone see that if you look at that, that's 2 oxygens and 4 potassiums? Easy to see, right? Now, do we want to have to draw this every time? No. So now let's talk about doing it over here. Okay, let's go to balance it. We'll look at the left side. We'll look at the right side. And I've got only 2 atoms here, so that's easy enough. I've got potassium and I've got oxygen, okay? And right now, I've got on the left side 1 potassium and 2 oxygens, and on the right side, I've got 2 potassiums and 1 oxygen. Uh-oh, well, this doesn't work nicely, does it? So which problem do you want to solve first? Okay, let's solve oxygen first. Doesn't matter which one you solve first. We'll solve oxygen first. Right now, I've only got 1 of them. So what am I going to have to put out front here? 2. Because it's always multiplicative. It multiplies. So this times that, well, what number is here even though we don't see it? 1. So that makes this. 2 times 1 is now 2. Now we have 2 oxygens. Great. The problem is now I also have how many potassiums? 2 times 2 is 4. So I solved my oxygen problem, yay, but I created a potassium problem. Okay, how do I solve my potassium problem? And obviously the answer is I'm going to put a 3 here, so I get 3 more of them, bringing this up to 4. Because we solve these by adding. A lot of adding when we do balancing equations. That's me being sarcastic. There's not. When we put a number in front of something, think of it like Happy Meals, right? Or whatever. If you get another one, you get everything inside multiplied up, right? Think of it like toy boxes, whatever. But the Happy Meal model of chemistry is a good one for me because I like Happy Meals. So how many of these do I need? 4. Not good. All right. Shh. So listen. Shh. This is a metal oxide. Okay, that's obvious because it's just a metal with oxygen. So of course it's a metal oxide. Why would I even mention this? Guys, why would I even mention this? Am I just wasting your time? Yeah, so this particular one is potassium oxide, but if you reacted sodium with oxygen, you get sodium oxide. If you reacted magnesium with oxygen, you get magnesium oxide, and zinc would give you zinc oxide, and so on and so forth. So, okay, that's obvious. The reason this is a special case is not this half of the reaction. This half of the reaction is like anything else, okay? Anytime you do a synthesis reaction, you do the metal and the non-metal, you put them together, you get that, great. But metal oxides are special. So we're going to mention that here. And if I didn't leave you enough space, we could even cross that out if we have to. That's okay, but we're going to make a note here, an important note. And then we'll show an example below. In fact, we'll use this example. Metal oxides are important because they dissolve in water to form bases. And I'm going to say they go aqueous. And then I'm going to write above that means dissolve, or I'm going to say when aqueous, because they form bases. I'll just say when dissolved in water. I changed my mind. Forget it. That was unnecessarily difficult. And this is one of your key cases to know, that this gives us a second synthesis reaction. So this is a synthesis reaction, right? Two things come together to make a new thing. Well, the cool thing about this is it will undergo a second synthesis reaction. So I like this example because it lets us show two synthesis reactions. The first one is what we call a binary reaction. One atom plus one atom gives you a compound. But the second case, and this is a case we should know, is now let's take this stuff. Let's take the potassium oxide and react it with water. And we're going to get another synthesis reaction. Now, this is not as easy to predict. In fact, I wouldn't expect you to be able to predict what will happen here in a vacuum. Does that make sense? I wouldn't expect you to just be able to figure this out. But I'm telling you that they form bases. And maybe some of you remember from grade 10 science what anion, what the negative ion is in a base. It has an OH minus ion. So the potassium is going to, and if you think about it, it makes sense because look, this has how many hydrogens? 2. Well, if one of them attaches to this oxygen, now they would both be an O and an H, OH. Does that make sense? So when a metal oxide reacts with water, the hydrogen jumps ship, and every water becomes an OH, and every oxygen on here becomes an OH. You get a hydroxide. But now, that means instead of having potassium oxide, we're going to have potassium hydroxide. Now, that's a new formula. So what are we going to have to do? Figure it out. Does that make sense? So this is a case I want you to know. I want you to know that metal oxides react with water to give metal hydroxides. And again, I wouldn't expect you to be able to figure that out just by looking at it. To be clear, nor did scientists. You know how they figured this out? By doing it experimentally. Does that make sense? By the way, we are going to do this experimentally tomorrow. We're going to blow up some potassium. No, we're going to do this as a demo. No offense, but I'm not sending you off to blow stuff up. But if the weather's nice, we'll go outside and do it because I prefer to do it outside because it's loud and sometimes sets the smoke alarm off. But if we have to do it in here, and then we can just do that. We know what charge potassium takes. What charge is that? +1. And does anyone remember what the hydroxide ion takes as its charge? -1. And in this case, I don't even do a table. They match. What's the formula of potassium hydroxide? KOH. And so we can go over here and put that there, and we're all good to go, except is this balanced? No. Let's take a look at left side, right side. Now we've got 3 things to worry about. Boo. We've got potassium, oxygen, and hydrogen. On the left side, how many potassiums? Yep. On the right side? 1. On the left side, how many oxygens? Careful, count all together. Yeah, we have 1 here and 1 there for a total of 2. And over here we have, and on the left side, how many hydrogens? And on the right side, easiest balancing question you'll ever do. Yeah, we have to double all these things, which are all there. We throw a 2 there, and now we're balanced.
Interruption, folks. On today's cafeteria menu, we have beef barley soup for $2, assorted sandwiches, chicken or beef tacos for $4.
You will have this so good by the end, don't you worry.
Thanks for listening. Have a great day.
So listen, we will redo this lots, but I want to make note. Look at me. Shh. I'm always going to tell you. Shh. Look, shut up. Look at me. Shh. I'm always going to tell you the difference between something you should be able to figure out and something that you have to know because it's a special case. Does that make sense? You need to know both, but the difference is this, I should be able to give you potassium and oxygen, and if you, you should just be able to work that out because there's only one way to put ionic compounds together. This is a special case. You have to know that this happens. So don't feel stupid if you don't know it. You couldn't have figured it out. You have to be told. Does that make sense? Go away. Have a great day. Be kind to one another. Well, don't. I mean, you're welcome to stay, but you may go away. If anyone wants to see how they did on their test, I would love to show you. Feel free to come and ask. We'll get those back tomorrow and take them up. Sorry? Mm-hmm. Yeah, you bet. Let me put them on that screen so I'm not broadcasting everyone's mark to everybody. All right, come on over. I think that's you. Yeah, there you are. So you did well. You did very, very well. A good showing. That's your overall. And you can see a strong multiple choice, 1 error. Did great in, what was part B? That was, why am I blanking? What was part B? Yeah, that's right. That was Lewis diagrams. No, D was naming. What was C? Well, let's look. Oh no, B was calculations and short answer, which you did great there. And then well over here, what did you not? Well, we'll see tomorrow. There's something you didn't do there that I didn't like, and then great and great. So great showing overall. Really good. Really excellent. Be delighted with that. I'm delighted with that. All right, give me a second. Just gotta find your...
No, that's 20. That's a 30.
Yeah, great showing. Like, phenomenal. And especially when you think, like, you joined us late. And so, of course, like, there's stuff that you had to kind of figure out on your own and stuff. So that's your overall. And then you can see section by section. You did great. And it makes total sense. Look where you lost the bulk of your marks was on a question of stuff that we did before you got here. You did very well. Good job. Let me just look and see who we're looking at here. There you are. Okay. So there you're sitting. So that's your overall. Good. Very nice. I'm happy with that. A rough-ish multiple choice for you. And that was kind of your weakest section. Everything else is better than that. Did very well in the kind of math and short answer of it all. Naming, still some issues. Like there's something you'll want to pick up on there. But yeah, a good mark overall.
If you think we made a paper, you think we applied? What? It's a question.
That was a question just begging to have the word technically in it somewhere. Okay. Let me see who you are. There you are. All right. So that's your overall, and then section by section. Pretty consistent throughout. A little weaker on the multiple choice than the rest. That's typical. That's normal to be expected that people usually struggle more with multiple choice than.
I can't see that number. I'm sorry.
No problem. I'll zoom out. I want to
Okay.
be like screaming your market people.
All right.
There you go, the highlighted one.
All right. Thank you.
Cool. You're welcome. Who do I have next? Hannah? Yeah, swing on by. All right. Oh, there you are. Really, really good. Really strong showing. Like literally, like, but even stronger than the grade represents because like 2 questions that we were pretty solidly burned by, and then everything else really strong. So really, that tells me there's like 2 concepts that you kind of didn't get, which on a test like that is gonna present itself. But like in terms of what I care most about, your naming really strong. So that's I think you had a blank, and that made me angry. You left, yeah, I was not happy with that. Asked me if I was pleased with your having left that blank. I was not. Did not care for it. But overall, very good. Yeah. Wait, can't wait. Really?
Yeah.
That's amazing. Let me see where you are. There we are. All right. Yeah, so rougher than I'm used to from you. Not kind of what I expect, but rough multiple choice.
Was it on Monday?
It was.
That's why I wasn't.
I know. So yeah, not your usual showing. So I was disappointed for you. Not in you, but for you. Because I think you usually show better than that. I wouldn't stress about it. You got a ton of course ahead of you. Not a big deal.
The part B, was that, which one was that one? Was that the one where I accidentally did covalent twice and I knew that as soon as I handed it in?
That was in part C, yeah.
Yeah, I know that. And then the first
Yeah.
one was the math one, and I didn't know how to get it.
But you did. You're psyching yourself out. I could see it. Like you know that stuff, so it's fine. So that's a disappointing turn for you. Good news is this will fade into obscurity. And you had some naming, a few weird moments, mostly pretty good. But on the whole, I think not a typical showing for you, like it's not one that has me worried. I just feel bad for her.
The first
doesn't
math
show your
test,
skills.
I got 49%.
That's a whole lot better than that.
And then I got 51 when you did the spelling test.
Well, there you go. Hi. You had a great showing. Very, very, very strong. Very well done. Really good. Yeah, great. Excellent. Just exemplary. Wonderful. Big fan.
Yeah, thanks.
Well done. Where are we at? I don't have you in here.
Bio.
That's what. wrong,
Also, I was
wrong
wondering-
class. I did know that. I do know that you're in my biology class. Sorry.
Are we able to finish the lab today?
Yeah,
Okay.
you bet. Yeah, I mean, it's annoying because I have one not here again. Oh, you were on my yesterday writers, right? I've got to put you in still.
Okay.
I will. I'll get to it today.
All
I
right.
just I fell asleep at my mother's last night, and that's where I graded your guys. So I just have to. I put them on a piece of paper, so they're on a piece of paper. I just need to enter them in here.
All right.
But I'll get them in a. Yeah. Did you want to see?
No, I already did, I think.
Okay.
For third period tomorrow, can we do the math?
Yes. Yeah. Oh, math test.
Yes.
Yes. So I'm going to book you in. And then, do you want some math help?
Yes, and I also would like to see my.
Great. Swing on by. And actually, Trent, am I a monster? Can I just push you tomorrow? Just, I'm not trying to be an ass, but just the idea of doing it, like setting it all up today and then setting it all up again tomorrow. I would love to just do it at once if I can. Is that okay?
I was going to suggest that too because I know Catherine.
Yeah,
was
exactly.
doing it last time.
Is that okay?
Yeah.
Thank you for being understanding. I appreciate that. I know it's annoying to have something stay hanging over your head. Is that you? Oh, that's the wrong class. That's why that's not you. Yeah. Hey, that's great. That's very, very good. Yeah, like just strong throat. Yeah, multiple choice a little weaker than the rest. That's totally normal. Like that's the typical state of things. Naming was pitch perfect. Drawing was pitch perfect. Yeah, that's great. It's very well done. Chem feeling comfy for you?
Yeah.
Yeah, it doesn't look like there's anything stressful in there for you. Cool. Love it. All right, let's get to it.